Yeah, please make it live.
So it's live now. Okay. Good evening to all the members of Tiblane and other participants present here in today's weekly Tibeto-Burman talk series. Our speaker for the session is Dr. Priyankoo Sarmah. He is an associate professor in linguistics in IIT Guwahati. And his research interests are phonetics and phonology of vowels and tones, TB languages, language technology development, speech perception, and speech recognition, to name a few. He has had published papers in LTBA, International Journal of the Asian Language Processing, and Journal of the Acoustical Society of America. He has also had papers in a lot of conference proceedings, and he has been invited for lectures across different universities of India. He's also a member in several organizations such as International Speech Communication Association, LSI, Association for Laboratory Phonology, IPA, and Interspeech, which is from 2018 Hyderabad. He's also a patent with his co-researcher, Mr. Prasanna Chakrabarti, Shantirani, and Devnath. Um, he has been presently teaching courses in IIT Guwahati, which are Writing Systems of the World, Perspectives in Linguistics, Issues in Tone Languages. And he has completed several projects on acoustic phonology and social linguistics from 2013 to 18. Currently, his project is development of speech interface for form filling applications in 5 Indian languages, which is yet to be completed in 2031. He has um, he has also supervised several scholars in his department, of which one of them has completed his PhD. And there are also other students other than those from linguistics. There are others as well from the same IITG as well. So I'd like to request our speaker for today, Priyankoo, to kindly deliver your talk. The Zoom room is open now.
Okay.
Thank you.
Okay, Manali, thank you very much for such an elaborate introduction. I'm going to share my screen now, so please let me know if it is visible. If it is visible, can you please give me a thumbs up? Fine. Okay. Thank you. Yeah. Okay. So today I'm going to talk about tonal acoustics and beyond the case of Mizo. So basically, my idea is to provide some background on how to do acoustic analysis on tone languages, tones in tone languages, and then I would like to bring in what we have found or what we have uh, uh, been working on in Mizo, and what are the outcomes. So the first two parts, oops, the first two parts, as you can see here, part one and part two will consist of tones and their acoustic correlates. Not too many slides, maybe 4 or 5 different slides there. Part two is acoustic analysis of tones, how to do acoustic analysis. And then part three and four would be mostly our works, me and my students who have been working on Mizo language very extensively for the last few years. To give you a further um, detail on the talk, so first I'll talk about in part one on fundamental frequency, and then I'll introduce creakiness and breathiness as part of tonal correlates. Then I'll go into talking about acoustic analysis of tones, how average F0 of tones help us in modeling tones, slope of tones, then duration of tones, and finally about F0 normalization. Part three, I'll talk about mostly Mizo, where I'll talk about the Mizo tone inventory, contextual variation, how tones interact with other tones, how vowels interact with tones, and how consonant interact with tones in Mizo, what we have found out. And finally, I'll talk about meso tone classification. So I'll talk about one particular methodology called quadratic discriminant analysis, using which, if we provide certain features of tones, the machine or the statistical method can automatically classify the tones into different categories. And finally, I'll just talk a little bit about a meso ASR that we have been working on for quite some time, and provide you a small demo of that. So this is the overall organization of my talk. So I'm planning to talk for about 40 to 45 minutes today. Okay, so the first part is tones and their acoustic correlates. Uh, so F0 and tones, and as most of you already know that F0 is the primary cue for tones. Please remember that like some of these ideas that are some of these items that I'm going to talk about must sound very basic, but I'm pretty sure that there will be some people in the talk who might actually require this information before we go into the further details or further complicated ideas later introduced for meso. So I'm going starting from the basics. So in tone languages, we all know that fundamental frequency is mostly the primary cue. That is, when we talk about languages like Chinese, Mandarin Chinese, or let's say Mizo or Angami, we know that fundamental frequency works for discriminating between different tone classes. Okay. So F0 is basically the rate of vibration of the vocal cords. So the vocal cords are located somewhere around here. And I got a video from YouTube, which I'm going to play now. And please let me know if you can hear the sound well or not, where a lady is trying to produce some fundamental frequencies, some sounds at different fundamental frequencies. And please notice the vibration of the vocal cords here. Monali, if you can hear it well, please give me a thumbs up, okay? Okay, in this video, what you have noticed is that okay, sorry about that. So what you'd notice in this video is that as the person produced higher and higher notes, the vibration of the vocal cords was actually faster. And that is what is captured, this faster rate of vibration of the vocal cords is what is basically captured in most of the pitch tracking softwares like Prat that we use to get acoustic values of tones. Okay, I'm going to talk about it in a little. Okay, so this is what you'll notice in a usual acoustic phonetic software, acoustic like analysis software such as Prat. You'd notice that there is a waveform, as you can see in this case here. Here is the waveform, and here is the spectrogram, right? And in this waveform, what you'll notice is that uh, on the spectrogram, let's start with the spectrogram. On the spectrogram, what you'll notice is that there are some dark lines, like you can see here, which are followed by some light lines, like, a dark and some dark lines and some white lines, etc. So these dark parts basically show that that is the time you had a higher rate of vibration of, there is a higher rate of air coming out of from your vocal cords. And when it is white, it means that there was no amplitude, there was no energy, and your vocal cords were completely shut. So at the same time, this corresponds with these waveforms. And these waveforms, the openings when the airflow is very high, where the intensity is high, these waveforms actually create these peaks, right? So basically, what we are doing in analyzing pitch tracking software for analyzing tones, if we are using it, what we are doing is that, what the program is basically doing is that it is basically trying to pick these different peaks and trying to see how closely or how far apart these peaks are to estimate the fundamental frequency or f0, which is basically basis of the tones, right? So we know in general that fundamental frequency or f0, which is supposed to be different for different tones, is basically the number of these peaks here that you can see divided by time in second. So I did something before I came to the talk today. I actually hand counted all the peaks that you can see from here to here, right? And what I know is that there are 57 peaks here in this sound, and the total duration of the sound from here to here is zero point 0.3 seconds, right? And this is the simple formula by which you, if you do this calculation, 57 peaks divided by zero point 0.3 seconds, you get 190, and that is basically 190 hertz is the fundamental frequency of this sound that I produced this afternoon, right? So uh, the reason I'm telling you this is because when we talk about the acoustic analysis of tones, the first thing that you'll see is that you'll see these fundamental frequency values such as 150 hertz, 180 hertz, and I want you to know what these 150 or 160 hertz actually mean. These are basically the number of times vocal cords are opening and closing in 1 second. And then these numbers may keep on changing from high to low as you speak. For example, if you are producing a very flat tone, such as the, my numbers are not changing. But if I am changing my pitch from a lower to a higher register, such as la, my these characteristics, my number of times vocal cords vibrate. Initially, it vibrates less, and then towards the end of it vibrates more, right? So this is what we are trying to capture all over our when we are trying to do acoustic analysis of tones, right? By the way, if you have any questions, or right now there might be some things that may not be clear for you, so I would like strongly encourage, if you want, please go ahead and ask the questions right away, write the questions right away, so that while I am giving a presentation, I can take some of the questions and I can answer those questions too. Okay, so what we have talked about here is that in most of the languages, in many languages actually, fundamental frequency is the fundamental, basic characteristics which define the tones, right? For example, like Mandarin Chinese, as I have told you, Mandarin Chinese has this high ta and rising ta, falling ta, and falling rising like ta. In all these cases, fundamental frequency is basically the primary cue in identifying the tones. However, that is not the case in all languages. For example, most of the Southeast Asian languages, what we know is that apart from the fundamental frequency, they also bring in some other phonation characteristics such as creakiness or breathiness, along with the fundamental frequency changes, which characterize some of the tones. For example, look at Burmese. Burmese has this low tone, high tone, and apart from that, it has a creaky tone and also a kilt tone, which is basically a glottal stop at the end. Right? I have provided the references down here. If you're interested, please go ahead and read those references. You can refer to those references if you have not already. If you don't have access to them, please don't hesitate to send me an email to ask for any of the references that I mentioned today. So second is the case of Hanoi Vietnamese. As we know, as many of us may know, that Vietnamese actually has 6 different tones, but including 2 specific tones which occur only in checked syllables, such as this T, where it is the coda is present, and these 2 are basically the special cases of tones which appear only in the checked syllables, and they are kind of shorter and with a little bit of different characteristics. If you look at the other tones, then you will see that apart from the normal level and mid-falling tones, they also have glottalized tones and broken tones, etc. So what we know is that while most of the languages that we commonly know of, they use fundamental frequency as primary cue, there are languages which use Apart from fundamental frequency, they use creakiness and breathiness kind of characteristics also as cues for identifying tones. And the analysis for those languages is going to be a little bit different, which I'm not going to talk about today, but it's going to be a little bit different. You have to, because you have to basically characterize the breathiness and creakiness in those languages. Okay. So in part two, then I'm going to talk about the acoustic analysis of tones now. So let's talk about a standard characteristic, standard case of tones where you have three tones in a language where the language, the tones are basically flat tones like ta, ta, ta. Right. Here, what you can see is that in the first case, this should be hertz, right? You can see that the first case, the tone starts at 200. In the middle part also it is 200. All throughout, more or less, it is it stays at 200 hertz, right? This is like, these are all examples, so they are not like what's going to happen in a real like level tone system. But I'm still going to give you this example as a for uh, to make it the story simple. Look at the here it is 150, 150, 150, here 100, 100, 100. So it is easy in these languages. If you want to characterize these tones, probably you'll just need to go ahead and provide the average value, fundamental frequency value. You calculate at the initial position, mid position, final position, and do the calculation that 200 is equal to 600 divided by 3 is equal to 200 is the hertz, is the average fundamental frequency, right? But this is unfortunately what happens is that the tone languages are not that simple. There are tone languages which look like this, right? Which have tones like this, which have rising tones, like which go from 100, 150 to 200, and they might go for 200, 150 to again 100. In one case, they might have a rising tone like this, and they might also have a falling tone like this. Right. In those cases, the acoustic analysis becomes a little bit more difficult because now only calculating the average tone is not going to give you a true picture. Because if you look into these two cases actually, both the rising and the falling tones, the average is exactly the same. So what do we need to do? We need to characterize the slope. We need to provide the information that one has a kind of negative slope and one has a positive slope. Right? The situation becomes much more complicated when we have a third kind of language where you can see that the tone basically starts from a lower register, goes high, and then falls down. There are languages like that. And then there is high, low, and high again. Right. So in other words, that only average, you calculating average is not going to be enough to do an acoustic analysis of tones. So what are we going to do? So look at this example that I have provided you, which is from a real speech. As you can see, in this case, you have the waveform here and the spectrogram here, and the blue line here shows basically the fundamental frequency that changes. Here you can see that this is the nasal part actually, not part of the tone. Here you can see that the tone starts here, goes all the way up to this point. Right? It's a rising tone. So what am I going to do? The standard procedure is that to take the average of the F0 of the tone, right? So what I'm going to do is that I'm going to first look at the parts where the tone begins. This is the part it begins. This is the part it ends. And then I'm going to splice this, the whole tone into several different parts and take measurements at each of these parts and then provide an average of all the points, right? Secondly, what I could also do is that I could also subtract the final point, this point, fundamental frequency of this point, with the fundamental frequency of this point and get a slope. I could get a minus number or a plus number. So this is the simplest way I can distinguish between a rising and a falling tone, because a rising tone will have a plus number and a falling tone will have a minus number. Right. So this is the basic of the tone analysis. This is what we are trying to do. We are trying to model. This is how we are trying to model tones by using acoustic measures. Right. Okay. So if there is any question here, I would be more than happy to take the question now. Okay. Okay. So the problem is that next problem that we'll find in acoustic analysis is that the speaker effects. What is happening with all of us is that your fundamental frequency, my fundamental frequency, Bijan's fundamental frequency, and all of you who are here attending currently this talk, probably all of you have different fundamental frequencies naturally. All of our voices have different levels, right? Different pitch qualities. So these physiological difference between all of us is going to be a problem when we are going to look at the fundamental frequency of different tones as a whole. Right. In other words, when I'm speaking or I'm producing a tone, I'm not only producing the actual fundamental frequency of the tone, there is a little bit of me also in the tone. Right. There is a little bit of my own physiological characteristics that is also included in the tone. As a result of that, it is very important that we remove the physiological differences that we see. So there are several methods to remove the speaker specific effects. One of these effect that we works well is a method called Lobanov or Z-score method, which performs very well. You can see that this particular work in Rose 1992 have shown that the fundamental frequency effects, the speaker effects in fundamental frequency can be best removed using the Z-score method. What is the Z-score method? Z-score method is actually very easy. What you do is that you take one of the points that you have just seen in the previous slide, like one of the points, subtract the average fundamental frequency and divide it by the standard deviation that you'll get from the as a byproduct of the average while calculating the average fundamental frequency, and you get a normalized fundamental frequency which does not have any of the speaker effects. Okay, I'm going to show you an example of meso a little later, where you can see how the speaker effect is basically removed. Okay, so this, what it does is that this results in some formant values, the hertz values that you have seen like 100, 200, etc. Now they are all going to go because of this normalization, and all you are going to be left with is a plus number, plus 1, minus 1, plus 2, minus 2, kind of very small numbers, because now there is no speaker effect, there is only tone information that is available there. Okay. Okay. So in a normal acoustic analysis, this is the procedure that I'll follow. I'll go for F0 normalization to remove the speaker effects. Then I'll calculate the pitch contour, right? Average of the pitch contour. What is the average pitch value? The slope, what is the slope that I get? And then I will also calculate the duration of the tones. So what is the total duration of the tone that I have with me? So in order to do a good acoustic analysis of tones, this is what I'm going to do. Now I'm going to go to the acoustics of mesotones. And the information that I have provided you just now in part 1 and part 2 will be very helpful, hopefully, in decoding what I'm going to talk about in part 3 and part 4. Okay, first let's look into the tone inventory of meso. So if you look historically, the tone inventory of meso, you'll see that there are actually, like, the people are divided between 5 tones and 4 tones. However, most of the people have agreed that meso is mostly a 4-tone system where you have a high, low, rising, and falling. Right. This is, like, basically seen in case of Wiedert, who has done an analysis of the Lushai tones. I forgot the complete name of the book. Lushai tones. Fanai, both in her MPhil and PhD thesis, she has talked about these 4 tones. Tsangte also, Madam Tsangte also has talked about high, low, rising, and falling. So these are the 4 tones that we know about. And in the following sections, I'll show you how to basically model these tones. One of the problems that we have found in meso is to find a perfect minimal set to get data, to get acoustic data from. Finally, we have been able to find, like, 2 sets, for example, the Thang set and the Vai set, wherein with the high, low, and falling and rising, in all 4 cases, you have 4 different lexical meanings. So this is what we are going to use for our mesotone analysis in the that I'm going to show in the following slides. So this is a work that me and my student Wendy Lalming Lui, we are doing together. It is under revision, acoustic correlates of mesotones. So, but if you are interested, I'll be more than happy to send you a copy of the paper before it is published. So this is what you notice for the four mesotones. Now you can see clearly what is the the rising tone. This is the rising tone here. This is the high tone. This is the falling tone here. This is the low tone. Right. However, look at the difference between female speakers and male speakers. Right. If you look into the male speakers' fundamental frequency, male speakers' fundamental frequency remains somewhere between 100 to 150 hertz. Look at the female speakers; they are like about 175 hertz to about 275 hertz. Right. So they're much more higher. So in order to look at the actual irrespective of sex differences, what are the mesotones? If we want to see, then again we have to go back and do our speaker normalization. So we did that. We did the speaker normalization, and now I'm going to show you the after normalization, what do we get for the mesotones? These are the four mesotones. Remember, I told you about the number. This is 1, this is minus 1.5. So now they have changed because of mathematical reasons from that 100, 200 to 1 to minus 1.5. And you can clearly see the models of the mesotones. So now we are assuming that this is what actually the meso high, falling, rising, and low tones must look like without any effect of the speaker, mostly in the purest form, if you think so. Okay. Okay, so now then our next question was that, well, that is fine. What when we are sorry when we are uh, obtaining these tones in isolation, what happens when mesotones basically interact with other mesotones? Right. So this is what we wanted to see in the mesotone tone effects. So there is another work which I would encourage, if you are interested, to look into. These are available freely online. So contextual variation of tones in meso, where what we have done is that we have recorded trisyllabic meso phrases, and each of these cases would have all the possibilities of mesotones. For example, high, low, rising, high, low, falling, etc., etc. In total, there are 64 such tone combinations that you could get. So we have all the 64 combinations in our work. And for each of these 64 tone combinations, we got 5 syllabic, trisyllabic phrases, which will result into 320. And each phrase was uttered by 3 times and by 4 speakers, resulting in 3,840 tokens. So now what we are trying to do is that we're trying to see what happens when we have a high tone before another high tone. What happens when we have a low tone before another high tone, etc., etc. So what we noticed here in this work is that what we see is that high and low tones are actually least affected by the falling tones. However, rising and falling tones get considerably affected by the falling tones. Remember that rising and the falling tones also need a lot of effort to change the tone contour from lower to higher or higher to lower. So that is being affected, as we have seen, in case of the higher, the rising or the falling tone remains with another tone following it. Okay, so we'll talk about it more, but I want you to look at this case here. So this is one of the cases where we have a falling tone here, right? And the falling tone is followed by a falling tone itself, a high tone, a rising tone, and a low tone. And you can see that the characteristics of the falling tone changes depending on which tone is there following the falling tone. So another thing to show that will be of interest to you to look at here is that look at the falling tone, the range of the falling tone. It falls this much here, but here it is almost like a flat tone. So the whole contour of the falling tone is somehow simplified in the when it is preceded by other tones. Here is the high tone. High tone, as you know, it is already a level tone in meso, so it is not going to change much. It is not changing much, irrespective of what is the tone that is there behind it. However, look at the rising tone. Rising tone has something very interesting happening here. When you have a rising tone followed by another rising tone here, right? It appears as a rising tone. When you have a rising tone followed by a falling tone, still the rising contour is there. But when the rising tone is followed by a falling tone and a high tone, it is no longer a rising tone. It becomes almost a low tone here. So when we looked into the literature, we found that already Vidert and Sangde has actually observed it, and they have said that, in the context of a falling high or a falling tone, the preceding rising tone loses its rise and it becomes a low tone. Now the point here is that, if it becomes a low tone, is it a tone sandhi? Some people have said it is a tone sandhi, and we have also argued in one of our works that it is a kind of tone sandhi that we observe in Mizo language. Okay, so uh, now, in the contextual variation, we found of tones, we found certain conclusions. We found that the anticipatory effects are less on the high and the low tones, as you have already probably noticed that what we have seen here. What we have seen is the carryover effects in meso are assimilatory. So whatever is the preceding tone, that tone's level is what the following tone tries to match. If the following tone is high, even if it is a low tone in the following it is going to go up a little bit and try to match the high tone. Right. Anticipatory effects, on the other hand, the preceding tone effect of the preceding tone is going to be tone dependent. If there are high tones, they are going to make the preceding tones low. If they are low tones, they are going to make the preceding tones high. So there is a dissimilatory effect. So there is a dissimilatory effect for high tones, but low tones, when they are low tones, they're going to actually lower the tone contour, so they're going to have assimilatory effects. So now my question, the question that we wanted to ask is that the low tones that you have just seen in case of this rising tone here, the low tones here, are they actually low tones, or can people hear them as low tones? That is what we wanted to find out. How do we do that? We can do a perception test. So what we did is that we took 20 unique, meaningful mesodisyllabic phrases, which would contain actually a low tone and a rising tone, which would become a sandhi low tone because of the rule that we have mentioned now. For example, we found these cases. For example, when you have lay, as in rising tone, it is soil. When you have lay, it is bridge. Right. So we follow it by the word white, which is var, which is high, and as it is a low tone before a high tone, nothing is going to happen. But in case of soil, because soil is a rising tone, this high tone is now going to make the rising tone a low tone, right? So this is what happened in our data. So we have now two cases here: the bridge, levar, which would mean now bridge, white bridge or white soil. But the low would be different because one is actually a low tone, and the other one is because it has transformed from a rising tone to a low tone. So our point is to see whether people hear these differences or not. After one female speaker, produced all these variations here, what we did is that we cut these lays, core, bull, and y, and we asked these 20 meso speakers to actually listen to it. So they listen to it and they have to give an opinion, like whether they hear bridge, soil, or both on a computer. So what we found is that we took 11 meso-native speakers, normal speech and hearing abilities, bilinguals, as you know, 24 to 35 years old. This is the profile of our subjects. So when we look into the results, what we noticed is that in terms of correctness, actual low tone is actually less heard as a low tone, while the sandhi, the one which is derived from the sandhi, is better perceived by the participants as a low tone. Similarly, the case of the other case also, where it is followed by a falling tone also, the low tone that is arising from a rising tone, that is heard always better. So this is the the red one is how many mistakes that they make, and two is something where they said that it could be both, lay, white, and sorry, bridge and soil, etc. So what we saw here is that meso speakers can actually hear the one which has transformed, which has become a low tone, as a completely distinctly from a actual real low tone. So F0 differences in the production test tells us that these meso speakers probably have already made another category for the low tones that have arisen due to a Sandhi effect. Okay, later when we are looking at so speakers also perform very consistently, in on average about 70% of correctness they achieved in performing these tasks. Okay, so this is not going something going I'm going to talk about right now because of time. So the summary so far: contextual variation of tones in meso is evident. We can see that in our work. There is this Sandhi pattern, which is rising tone becomes a low tone when it is followed by a high or a falling tone. However, in perception, the low tone, the canonical low tone, is not equal to the low tone which has arisen due to the Sandhi fact, right? Okay, so in the next part, so we tried to look into these different effects of tones, right? So now we wanted to see whether the mesotones are affected by the vowels or not. So for that, what we wanted to do is that, so again, so this is a very interesting concept because it has been shown in different languages that the difference of vowels, whether you make a high vowel or a low vowel, that actually has an effect of the fundamental frequency. And in case of tone languages, it is also, this is called intrinsic fundamental frequency, or IF0. So in case of tone languages such as Standard Chinese, like Cantonese, etc., also, we have seen there are effects of the vowels on the tones. So this is a problematic thing, because if you think about it, a tone language speaker is actually looking at making a tone at a certain fundamental frequency. However, the vowel is actually inducing one fundamental frequency. So then he has to or she has to negotiate between these two factors. How long does he or she take to negotiate between the vowel induced fundamental frequency and the actually tone specific fundamental frequency? That is something that is of interest to us. So we looked into that. What we did is that we asked people to replicate the tones in real meso words, such as lay word, bell word, as you can see here, like bell, and then following that they should say ah. So you say bell, then they should say ah, etc. So they repeated all the vowels after the production of each actual lexical tones. And in total, from 8 meso speakers, we have collected the data where they have produced this a, o, e, I, u, the 5 meso vowels with different tone characteristics. One of the problems is here is that there are no actual linguistic words which are associated with all the 4 tones in meso with all the 5 vowels. So that's why we had to go for this another method where we'd replicate the tone. And this is an accepted methodology in our field of work. So when we look into the results, these results are amazing. Here you can see that, in case of the high tone of meso, you can see that here about 25% of the duration the high tone becomes level here. However, if you look at the initial part, the initial parts are going a little bit haywire depending on what is the vowel that you have on which the tone is being spoken. So if I zoom it up, you'll see that the E and the U vowel have actually made the fundamental frequency raised, whereas a vowel or the O vowel have actually made the fundamental frequency a bit lower. So if it is a high vowel, it is going to pull the fundamental frequency up. If it is a low vowel, it is going to lower the fundamental frequency. And it is not until about 20% of the total duration of the tone that the speaker has a control over the real tone specific fundamental frequency here, and starts producing tone specific fundamental frequency. So the same pattern, I'm not going to go over all of this one by one because the same pattern is noticed in all these cases. Another important thing that you would notice here is that as you have higher register in the higher tone areas, the difference is much more significant. When it goes to the lower areas, the difference is actually diminished, right? So that is also a consistent pattern that we have seen in our data. This is in case of rising tone, it is the same pattern that we notice. Okay. Uh, so the the point that we have concluded here is that we see IF0 or intrinsic fundamental frequency patterns in meso. High vowels induced higher fundamental frequency, low vowels induced lower fundamental frequency, etc. So is the fundamental frequency IF0 equally distributed along the duration? No. IF0 differences are basically subdued by tone specific values as the speaker tries to reach the tone target, so which is about, as it is happening in these our cases, about 20% of the total duration. In case of anticipatory effects, high and low. Okay, sorry. So this is not okay. So finally, we tried to look into the mesotone and the consonant effects in one of our recent works, where what we have done is that we tried to see if the change of the consonants preceding a tone basically changes the fundamental frequency or not. This answer to this question is a little bit obvious because we already know that there are tone consonant specific effects that are there on the following tones. So this phenomena is called CF0 or cointrinsic pitch phenomena. That is the effect at the vowel onset of the VOT differences that are preceding the fundamental frequency. I'll just go into the details. Here we have taken 10 meso native speakers and we have taken these CV non-word syllables and asked people to produce these, let's say, like pa, pe, po, etc. in all different meso tones. And when we look into this, this is what we notice for the for different consonants. So if you look into these cases, these are falling, high, low, and rising tone contours. And let's look at the beginning of these contours. What we'd notice is that whenever we have ba or the, the fundamental frequency begins at a lower register, and then it again takes some 25% of the total duration to become a tone specific fundamental frequency. Again, when you have some aspirated consonants preceding it, the fundamental frequency begins at a much higher range. So this is what is happening in all the cases of the meso tones. Whenever there is an aspirated stop, the fundamental frequency begins at a higher register, higher area. Whenever there is a voiced consonant, it becomes much more lower. And finally, it merges at about 25% of the duration. They all merge into tone-specific fundamental frequency. So what we see here is that there is a clear evidence of CF0 or CF0 in meso, and where voiceless aspirated stops, voiceless unaspirated stops, and voice stops, they are they have different effects. Voiceless aspirated stops raise the fundamental frequency at the beginning. Voiceless aspirated unaspirated stops don't have that much effect, but voice stops again depress the fundamental frequency. This interaction happens at a phonetic level, and it goes on up till about 20% of the total duration. So if you are modeling tones with different consonants, it's always a good idea that you don't take the first 20% or 25% to get the real tone specific values. Before the 20 or 25% of the total duration, you have vowel specific and the consonant specific, onset specific values of the fundamental frequency. Okay, so this is my last part, and I'm sorry I'm going over time now. It's already 45 minutes. So I'll try to be very quick in this part. So the last point is that why are we doing all these studies? Why are we doing all these acoustic analysis, beginning from looking at meso without any context, looking at mesotones with context, with different consonant and vowel context. One of the reasons we are doing it is to get a better picture of what actually these tone characteristics are. right? One of the ways we have said that we can capture these tonal characteristics is by taking the average of the tone contour of the fundamental frequencies. Then um, one of the ways that we I want to introduce right now is to determine the trends of this pitch contour that we are talking about, whether it is like level, it is falling or rising, is by changing, transforming the normal fundamental frequency values into something called the discrete cosine transform method. So this is a little bit complicated method, so which I'm not going to discuss in detail now. So I'm just going to tell you that this method gives you three values, which are the first three coefficients, which are called C0, C1, and C2. The C0 of the discrete cosine transform, when you run the pitch contours of a language through the discrete cosine transform algorithm, then you get the F0, the mean F0 of the contour. C1 and C2 provide information about how the slope of the fundamental frequency contour is going to be, right? So from the discrete DCT method, we can get three different values, C0, C1, and C2. C0 provides how the average fundamental frequency contour looks like. C1 and C2 provides information about how the slope and the fundamental slope of the fundamental frequency looks like. And that is important in case of a language like Mizo. As you can see, their high tone is level, which is captured by C0 here. But the rising and the falling tones are, of course, rising and falling, which will be captured by C1 and C2. So we can go for an automatic classification method. In this automatic classification method, what is happening is that we are trying to train the computer. We are going to tell the computer that look at all our cases of Mizo cases of high, low, rising, and falling. And I'm providing you the C0, C1, and C2 values along with duration values. Try to see if I give you a new mesotone, would you be able to correctly identify whether it's a high, rising, falling or not? So this is called a QDA classification method, or quadratic discriminant analysis. The idea is to, given certain values such as C0, C1, C2, or duration, how well a new tone can be classified into a new category. So if you look into the what we have done for Mizo, what we have seen is that when we provide only C0, and if we provide all the mesotones, then what we find is that the accuracy is actually only 27%. Right. However, as we add more of the features, C1, remember the slope feature, C2, again slope feature, the accuracy increases. So when we finally provide all the information about slope and average pitch contour, 90% of the times the machine is able to clearly recognize mesotones. If we add duration information also along with it, the accuracy increases to about 94%. Right? So now what we are doing is that we are asking the machine to automatically classify mesotones. I'll give you a mesotone, tell me what tone it is. So why do we do this classification? We do this classification because there are some practical applications, right? There are in tone languages, in tone language ASR systems, like for example, the Google voice that you are using. If it is done in tone languages such as Chinese, etc., what we see is that recognizing tones is one of the biggest challenges. In one of the studies that we have found, that in Mandarin Chinese, the errors that these automatic speech recognition systems cause is caused by wrong identification of the tones 70% of the times, because of the wrong identification of the tones. So here what I'm going to do is that I'm going to show a small based on all the studies that we have done on Mizo. What we have done is that we have made a automatic speech recognition system for Mizo. Now in this case, what I'm going to do is that first I'm going to produce the word isol into our system as with the right tones, which are high tones. Then I'm going to do with wrong tones, and you can see what the results are. You have to be a little bit patient because this is going to take a little bit more time than. Here we go. If you hear the sound, please give me a thumbs up. Isol, right tone, so right recognition, isol. Now I'm going to intentionally produce a wrong tone. Isol, and it is going to give me a wrong output. So I'm going to again try and produce a wrong isol with a wrong tone again. Isol, absolutely wrong tone, again a wrong output. And lastly, I'm trying to do marcha ro with a more or less correct tone, and let's see what happens here. Marcha ro, not very good, but still it gets it and it correctly identifies. So what we have done in this system uh, now, oops, sorry. What we have done in this system now is that we have actually embedded the information about the tones in Mizo. And as a result of that, oops, I think I'm missing one slide here. Sorry about it. Uh, One sec. No, sorry. I think I'm missing one slide there, where I wanted to refer to this work that we have done. So what we have done in this system is that after we have built the system, we have added some tone information with the F0 information that we have talked about, found out through the acoustic analysis, and we have added it. And as a result of that, this system now works. This ASR system now works much better because it has tone information. In fact, in many cases, when it is in a noisy condition, because we have tone information there, the recognition system works even better. Okay, so the last two slides are missing, so I just have to conclude here, and I'll just conclude the maybe impromptu. So the reason for what I want to show you here is that when we are doing work, when we are doing on work on these Tibeto-Burman languages and on tones, etc., there are too many things that are not being done, such as these interactions with vowels, tone interaction with vowels, tone interaction with tones, etc. So these are very important information. These give not only the insight into how speech is being planned in the mind of the human being, but also it helps us to have practical applications of what we are doing. And my idea of today's presentation was to show you that the acoustic analysis that we have done not only gives us information about how our meso speakers are producing tones in different contexts, but it also helps us to build systems which would be for public good, such as an automatic speech recognition, as you could see on the screen right now. So with that, I'll stop here and I'll take your questions if there are any. Thank you.
Thank you, Priyankuda, for your wonderful talk on acoustic studies in Mizo and beyond. It was very extensive talk on mostly on the challenges of F0 variation, and also in terms of identifying the right tone. And you have correctly shown different methods and techniques, especially stimuli test and the last one, which is auto speech recognition, which helps in identifying if the tone is right or wrong. I'm sure there will be questions from the participants. So you may unmute yourself and ask questions, or you can also type your questions in the chat box. The choice is yours, and the room is open for discussion now. I think there is a question from Viko Kotsu, and she asked, what are the things we need to look at acoustically to analyze disordered speech, comparing it with normal speech?
Yeah. Hopefully, I'm audible.
Yes, yes.
Yeah. So, I mean, disordered speech is a completely different domain, and it depends on what kind of disorder that you are talking about. So there are disorders such, I mean, like, what kind of disorder would be, it would be better to know what kind of disorder that you're talking about before going on to it, because there are some disorders by which like people are not able to produce the correct tone. Right? Are you talking about those disorders, or if you're talking about like complete motor disorders which does not allow or has certain like shortcomings in the speech. So I think it all depends on what kind of disorder you are talking about. It is a very big uh, question, and I think I may not be the best person to answer that question also.
In that case, I'd like to request Ms. Viko Kutsu to kindly specify which particular disordered speech are you talking about. You can unmute yourself and ask the question also.
Yes, sir. Hello.
Hi.
Uh,
Vic-
Hi, sir. Yeah. I actually wanted to know whether people who stammers or who stutters, like how can we acoustically analyze their tones or their or any vowels or consonants while comparing it with normal speech?
yeah, I mean, I would start with the basic, the just the way we do it with like the normal speakers. Those are the analysis that I'll do, and I'll try to compare
Mm.
with a normal population, right? Normal speakers population. However, there are conferences which are specific to this theme, and also there are sessions of conferences which were on stammered speech altogether, right? So
Okay.
I just encourage you to look into that. I still don't think I'm the right person to talk about stammered speech.
Okay. All right. Thank you, sir. Okay.
Sorry. I think I have
Monali, you're muted.
I think I have confused people enough that there is no questions.
Yeah. There are questions. Dr. Temsu has a question. You can unmute yourself and ask the same question.
My question was in the ASR tests that you had, was it recognizing words at word level, or were you entering
No,
phrases as well? Word
word.
level.
Yeah.
Okay.
Yeah, but we also have a study done on sentence level also, which is somewhere on the internet. You can look it up, like
All right.
meso continuous speech recognition something something.
Okay. All right. Yeah.
Yeah.
Okay, thank you, Dr. Temsu. The next question is from somebody I'm not able to identify. It's with the name iPhone. And the question is, did you consider vowel length, also globalized coda?
Glottalized coda maybe.
Yeah, glottalized.
Yeah, did I consider vowel length? I did consider vowel length because meso has a distinction between short and long. So we did for example, the examples that I gave first, the two sets, the vai and the thang sets, they are of the same vowel duration actually, both short. Did I take glottal stops? I have not looked into glottal stops because I really want to, or is it Madam Thangi? I think it is Madam Thangi probably. Anyways, so the glottal, because we really want to do the work on glottal stops, the influence of the glottal stops on on tones. Probably we'll do it within this summer. We have the data, but we are just we could not finish it up earlier. But that is an interesting question, and it's a very interesting subject also. Thank you.
Yeah, I think it's Dr. Changte ma'am. She's already unmuted. You can ask your question.
There is
You
anymore.
can ask it. Yeah.
Yeah, can you hear me?
Yes. Hi.
Yeah, happy
Yes.
Bihu.
Same to you.
I'm still waiting for my pita.
Yeah, I'm waiting
Yeah,
for mine too.
yeah. Actually, I'd like to discuss this with you in length later. If you can send me the article so I could read it up.
Oh, yeah.
Yeah, because like I noted, you know, there's the word you put greasy. There's actually two, because it's a verb. It's either tang or tang, and if it's tang greasy, that's a rising tone with a long vowel, and if it's tang, it means a greasiness. So it's nominalized. So there are actually two different words with two different tones.
Okay.
So I just want to point that out.
Oh,
And I
thank you.
think the one you have on the example is greasiness,
Right.
tongue. So that should be a long vowel. And also regarding the glottal, final, glottal coda, actually in my analysis, I phonologically, I treated, glottalized stops as actually a tone feature, because you have words like jia, which means to soak, and that's a low tone. But then you have jia, which means exactly. And so normally when you have a glottalized coda, it's always low tone. But when you have words that are not low tone, then they are not actually lexical words. So I've made a list of those, and that might be interesting to look at, from an acoustic point of view. So
yeah, I think.
But
I think one person who would really appreciate it is Wendy, because I think, yeah. So we'll probably we'll just contact you together.
yeah, and then also there are morphologically conditioned tone changes, and I'm actually working on a paper on that. So yeah, David Peterson is I think ready to kill me because I haven't sent it to him. But when that comes out, I'll send it to you.
Oh yeah, that'll be wonderful, because there's also, that is also a part of Wendy's dissertation. She is also doing something on that. So
because it has nothing to do with the environment,
right?
But tones change, and so that's what I'm looking at. So
right.
Okay, but yeah, that was really interesting, and yeah, it'll help for me to look at the paper. So
yeah, sure. I'll try to send all the papers that I mentioned here.
Yeah. I think you have my email, right?
I do. Yeah.
Yeah. Okay. Yeah. Sorry for the typo. Globalized. Should be glottalized. Yeah. Okay.
Thank you.
So yeah, enjoy your bihu.
Thanks.
Yeah.
Thank you, Chamta ma'am, for that question. Do we have any more questions from the participants? Dr. Haukip, would you like to ask any question?
Yeah. I don't have any specific question because I've just come back from Manipur, and I'm kind of I'm not linguistically in tune as of now, but I'm more interested in how do one find out how to identify and register tones from those of contour tones acoustically. So can you highlight something on that, the difference of acoustic evidence for register tones and contour tones for mizo? Yeah.
Yeah. So as I have shown in the first few slides, maybe right? So we would assume that something which is remains flat is basically a register tone, and something which changes its tone dynamics or F0 dynamics is going to be a contour tone, right? So if you do that, then probably you'd look for that slope. If the slope remains zero, or there is no deviation in the slope, then it is going to be a more or less register tones. But it is difficult to say so. The reason being is that if you look at the mesotone here itself, let's take these two examples. Look at the high tone of meso. Meso high tone is actually going up a little bit up. Oh, I don't think you can see it, right? I don't think, can you see the screen? No.
You have stopped sharing.
Oops, sorry. Yeah. So here, if you look into the, now you can see it, right?
Yeah, yeah.
Okay. Now, if you look into the meso high tone in these cases, then what you will see is that it actually does not stay exactly flat. In other words, if you do the slope calculation, you will get some amount of slope here, right? Because it starts to descend towards the end, etc. However, it is a very relative kind of measurement. Like you want to see it in relation to the other tones that you see here, right? And also perception is another, your own intuition or perception is another big factor which actually helps you to decide whether it's a register or a contour tone. Acoustically, you can be correct to a certain extent, but you would not get a zero kind of value to show that there is almost no slope, because there is going to be slope anyways, one way or the other.
Is there any relationship between contour tones and the quality of the vowels? So some of the vowels which are attached with contour tones either tend to be either long or diphthong. So is there some sort of relationship between the vowel quality and what do you call contour tones?
No, I mean contour tones usually require more times to like you know materialize, right? So that is one of the reasons why vowels associated with contour tones are actually long, right? And in meso kind of cases, you'll also see that diphthongs are long. Sorry, the diphthongs also have no, long tones also have contour tones also are associated with diphthongs, etc. Right. So I think one thing is sure, that diphthongs require more time to realize, at least 130 milliseconds according to some studies. Right. So as a result of that, a short vowel will not be good enough for long tones or dynamic tones to be to host dynamic tones. Dynamic tones require this physiological movement from one level to the other level, which is much very complicated for a short duration. I think there is there are quite a lot of studies on that. For example, Ishu's study, he has shown that how much is the minimum time to make these tone changes in language in Mandarin Chinese. So such works are not done in our languages, but I think we all should do such works also.
Yeah. Have you looked at the difference between long and short vowels in rising tones in meso? There are a few minimal pairs. Like tongue is trap and tongue is greasy.
Right.
And gir is curly and gir is to return. And those are definitely minimal pairs.
Okay. So minimal pairs are can I have the whole set? No.
If you look in my dissertation, I've listed them. So otherwise, I can send it to you.
No, I have your dissertation.
Yeah.
Yeah. So, but
yeah. So where I've given the minimal pairs.
Okay. So you complete sets, right? Oh, 4
Yeah.
different.
Yeah.
Okay. Yeah. I don't know why I missed that. But thanks for pointing that out there.
Yeah. Because I think in the short vowel, and this, you get this only with if the coda is vocalic, like, you know, you have L's, R's, and, you know, the nasals.
Yeah.
And so the final nasals absorb the rise. So
Yeah, right. So the rhyme is actually like, you know, the vowel plus sonorant coda, right?
yeah.
Yeah.
So I'd like to see the, you know, the difference in the, you know, in the codas, you know, where the tone lies. I don't know if I'm being clear. Yeah. Okay.
So can you just elaborate that a little bit? So for example,
like curly is gir, and to return is gir.
Mhm.
So it, you know, it's going from, you know, low to high.
Yeah.
So I'd like to, you know, compare the contours, you know, with respect to the coda.
Okay. Yeah, but in the second case, it sounds like a longer, like,
yeah,
you know, contour,
gir.
right?
Yeah, gir. So it seems like the tone ends on the, you know, the coda, but
Right.
gir, the vowel carries the tone.
Vowel carries the tone.
Yeah,
okay.
and gir, it, you know, it shares with the coda. That's my perception. So it'd be
Right.
interesting to see the, you know, the difference. And same with tongue is a trap, and tongue is greasy.
Okay. Right. Thanks for those. That's really interesting to look into. But I think we have
Thank you.
probably the data.
Yeah, I think there is a question, one more question from Normada Dule. I think it's a girl, right, Normada. Um, so she says, I have a question. Does the voice of the person affect the results? Some might have had more frequency than the others.
Yeah.
Normada, you can unmute yourself and ask the same question to be more specific.
Yeah. Hello.
Yeah, hello.
Yeah.
Am I audible?
Yes.
Yes, sir. So, good evening. So, I have this question that while doing the process, you might have found that some people have had more frequency,
Yeah.
you know, like even among the girls, there might have had people, there might have been the girls who had more frequency than the others. So, in that case, how do you work on that thing, you know?
So because that is why we do this speaker normalization, which I mentioned to you, that Z-score
Okay.
speaker normalization. We normalize for each speaker's effect. Right. As a result of that, we get this kind of contour that you can see on the screen right now, I guess, which is like, you know, after the normalization.
Oh, okay. So is this the result of one particular person?
No, it is the result of all the persons that we have taken in this particular work.
Okay, okay then. Thank you so much.
Mhm.
I think there is a hand raised in Tangi Changte. Yeah. Or was it for the previous question?
Yeah, it was for the previous question. Thanks.
Okay. Yeah, I saw Temsu also raising hand. I think he has a question to ask.
Just not exactly a question, but just I when this vowel effects, high vowels having more tendency to have higher F0. Just reminded of Vijay Krishnan's paper on loanwords, where he makes this claim that there seems to be some evidence where in Mizo as well as in Angami, where in loanwords with higher vowels take high tone, and lower vowels take the low tone. So I was just reminded of that particular point from his paper. I have on this small question with regard to this uh, perception test that you had, where you cut out the first word and then you presented it to the informants. So wouldn't cutting out the word and taking it in isolation, wouldn't that, I mean, I was just looking at phonetic versus phonology issue here, because you're taking something out from the context. And so once you take it out of the context, then how does that work? I mean, that the perception test.
Actually, so what happened is that when we presented it, we again presented it in a single, how do I say, frame.
Okay.
The frame was constant, but the word was the only one which was changing.
All right. Okay.
But if I'm if I have mistaken, I don't know. I have to again consult the paper myself. I forgot. It's been 3 years or more. Yeah, let me. But if I remember it correctly, that is what we did, and it's precisely because we had a problem with that out of context. Because when it is out of context, you basically don't have anything to relatively look at.
Right.
Any other question?
Right. Please unmute yourself and ask questions.
If there are any.
Yeah.
I see two Bijan Kumar.
Yeah, I think one is from the laptop and the other from mobile phone.
Oh, okay.
Yeah, for a while my laptop got hanged, so I was not able to do anything. So I joined from my mobile also.
Okay. No more question, I guess.
Dr. Mary, did you have a question? You can unmute yourself and ask.
Oh, Mary, maybe not.
Yeah, before we close, maybe a quick question. How much, so with regard to the contour versus level tone, I mean, phonologically, okay, it's, I think, much easier to make this distinction of contour versus level. But in terms of phonetics, so if you have a rising or a falling, because even if you look at level tones are not exactly level. They still have some kind of a fall or, some movement. So I was just wondering, like, how much of a fall or how much of a rise, is there any literature on this where you can say that, okay, this is a fall or this is a rise? How much of it would you consider it to qualify as a rising tone or a falling tone from I don't know, maybe a phonetic aspect?
No, I think there is literature which tells you what is the just noticeable difference between something which rises and something which falls. I mean, at which is a function of again the duration also, right? So at a given duration, how much rise or fall is perceptually distinguishable for the people, for the speakers. I think that is what finally it will boil down to. If people can hear the difference at a given duration, then I think it is possible to call it this one. So similarly, the same problem was actually there in analyzing certain tone languages, if a tone has, let's say, 50, 170 hertz, and the next tone is, let's say, 175 hertz, do we actually know, that these two are heard as a different tones, or they are considered as similar tones? So if we look into the literature, you'll find that human beings can be sensitive up to 0.5 hertz of tone, 0.5 hertz of fundamental frequency differences, even though 4 hertz or 5 hertz is shown as the norm, right? So, but there are cases where people are shown that 0.5 hertz difference is actually imperceptible to people. And interestingly, contrary to popular beliefs, tone language speakers are worse in distinguishing between small F0 differences than non-tone language speakers, because tone language speakers always look at F0 differences phonologically, but non-tone language speakers usually don't. So I think the whole question would boil down to human perceptual limits.
All right, thanks.
Yeah.
Right, that is very interesting to know as well. If there is no further questions, then I'd like to request our Joint Secretary, Dr. Bijen Kumar Singh, to conclude the session.
Okay. Thank you, Dr. Monali. I would like to thank Dr. Priyankoo Sarmah, IIT Guwahati, for accepting our invitation for this invited talk. So thank you very much for accepting our invitation, and all the individuals who have joined today's talk and who were engaged in discussion sessions also. Dr. Pokthang Haukip, Dr. Tem Shu, and Professor Thang Yi Changte and other members. I thank them also for engaging in the discussion. So I thank everyone for making this session interesting and very engaging. So yes, with this note, I thank everyone, and we conclude our today's talk here only. Thank you very much. Thanks, everyone.
Thank you.
Thank you.
Thank you, everyone. Bijen.
Thank you, sir.
Thank you, Priyankoo, for the wonderful talk.